right, so I'm going to work out the third order pathways now. So for third order, we have this sort of some frequency generation version. But the idea is you would have 3 arrows pointing upwards, right? And you would end up writing down your pathways like this. There's only one. Assuming that we start in the ground state, I need 4 lines, of course. Then we're going to go up on the left because we can't go down on the right. Up, up, and the signal goes like this. So there's going to be one excited state, another one, a third one, which could be, we don't know necessarily what kind of system we're dealing with here. And then eventually the system gets back to the ground state, or otherwise this would not be a diagonal, a population term. Right? So you could draw that, for example, with energy levels this way. Right? And you would go up, 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 and get a signal like that. And then look at what the coherences are. So the coherence in this position, in this time, is omega A0, omega B0, and omega C0. So those are the 3 frequencies that you could have. If you did an experiment like this, you might imagine fixing the time delay, maybe here and here, and scanning this time delay. That would cause a signal to oscillate at the frequency omega A0. And when you do the Fourier transform, you'd have the detected signal that you got from your spectrometer as a function of your excitation frequency here. You could do it a different way, where you fix this time delay and scan this one. Right? Maybe you move both these pulses earlier in time, and then you could get this frequency correlated with the detection, or any other combinations. So as I said, this is not an experiment that I'm familiar with people doing in the time domain with all 3 fields. So John Wright, I'll put some references to people. John Wright and David Klug, Paul Donaldson have done kinds of experiments where they only go through pathways involving coherences, right? Just a little bit like second harmonic or some frequency spectroscopy. And when you only go through coherences, your signal comes only from the different coherences that you have and not from any population terms. Right? And so this is one such pathway that has only coherences. All right, so let me show you some of the other possibilities. Now we have to start adding minus signs. So the signal will be, let's pick one. I have a pretty good way of writing it over here. So we had one minus sign, we'll put it with the K2. And remember that we can always multiply everything by -1. So this signal is the same as minus K1 plus K2 minus K3. It's going in the other direction. We're not going to treat those as different. All right, so we have the arrows again. So up to the right, up to the left, and up to the right. And then we put them on our diagram. All right, there's going to be a bunch of them, obviously, because you can move them from side to side. And now that we have 2 different signs for the arrows, that's going to give us quite a lot of options. So let me write down a couple of them. One is that we start up from the left. Now, it's always going to be that way because we're assuming that we start in the ground state. If we could start in an excited state, then there'd be more pathways because this arrow could go out and go down. So for example, and there's a kind of experiment that my group and some other groups have done, which is that you use the 2D experiment as a probe of something else. So you excite a molecule, for example, with a visible pulse. Maybe you cause it to break a bond, and then you shoot your 2D spectrum at it, 2D sequence at it. It's possible, and in some cases it happens, that when you do cause a photodissociation, for example, that some molecules, some vibrations are in the excited state. That means when you come along with your probe, there's going to be new pathways that come from going down from the first excited state, for example. All right, but you can handle that. There's nothing mysterious about it. You just have to keep track. All right, so then this is when I'm going to write a few of the hypothetical pathways. So we go to A, then we go back to ground state, Then we have to go up again, K3, that's going to come in. And then we could go back to A again. We could just keep going back and forth to A. And then we end up in the ground state. So this is like a pathway you would be able to see in a two-level system because I only have two levels involved at all. All right, so that's one possibility. Notice that the coherences are omega A0, omega A0, same sign. What do I mean by sign? Of course, omega A0 means the energy of the A state minus the energy of the zero state divided by h bar. So this is the same sign as this. And the population is on the ground state, which is to say that this signal comes from molecules that are not excited to an excited population. When you compute the whole signal, you have to add all the pathways together. So there'll be another pathway where they are, which we could write down right now. This one's going to look very similar because we're in the ground state. We go up on the left to A, but then we take our arrow, we slide it over, and now we're going up on the right-hand side to A. That puts us in an excited state population, whatever this is. All right, and then we have a choice. Where does the K3 go? Does it go here on the left or does it go here on the right? Let's do it on the right for now. So it brings the A on the right back down. And then our signal is always this one. And we end up with this. So what you'll notice is the frequency of the coherence is the same as this one. And so is that. But the population is on the excited state. So this looks like we're getting emission at the 0A transition by shooting light at it. So we call this the stimulated emission pathway, which we discussed when we were talking about our when we talked about our our pump probe experiment. What we're going to do now is we're going to look at another pathway when we don't have only two levels, A and B. We're going to have maybe A and 0. We're going to have B too. All right, so let's do that. Actually, you know what I should do? I should finish this other possibility. So the other possibility is we have everything the same, because we went up on the left, up on the right, and now we moved K3 over, so we go up again. So we get B, A. Then the signal will come from B going back to A. Why not 0? Because A0 would be a coherence and that trace would be 0. So here we have a frequency omega A0 for the frequency in the first coherence time. We have an excited state population. And then our signal that comes out is the omega BA frequency. Right? And so if this is a vibrational system, this frequency will generally be less than that frequency because of the vibrational anharmonicity. And we will see an excitation at a low frequency, or sorry, a higher frequency and detection at a lower frequency. This could also apply in electronic spectroscopy where there's not usually such simple rules about this. If it was a particle in the box and this was like a ground state transition, this was an excited state transition, then this transition would actually be bigger than this one. And you would see the detection at a higher frequency than the excitation because the energy levels of a particle in the box get farther apart as you go up. So we call this excited state absorption. So to make contact with the transient absorption viewpoint, this has to be called the ground state bleach. There's no other option. And so when you add up these pathways, notice that the number of interactions with the ground and excited state in both is exactly the same. So these two pathways contribute identically to a signal as long as nothing happens differently in the terms of the dynamics on this state versus this one. All right, so for vibrations, it's very common that you can make that assumption because the exciting a vibration doesn't have a huge impact on the world around it. Certainly going back to the ground state has no impact on the world around it. All right, but the problem is in electronic spectroscopy, as soon as you excite an electronic molecule to an excited state, a molecule to an excited electronic state, the charge density changes, the dipole moment probably changes, and the interaction with the environment will certainly change. And so there will be a different dynamics that occurs in the excited state than the ground state. These two are not going to be the same. There could be a Stokes shift. If there's a Stokes shift, then the frequency that you stimulate emit isn't going to be the same as the absorption spectrum that you would get, right? And so all this comes through in pump probe, 2D spectroscopy, you name it. All right. So far what we've done is we've worked out a couple pathways that show you what happens when you excite a ground state transition and then an excited state transition here. Here's where I'm citing by ground state transition, I mean a fundamental transition to the same transition here, same type of mode, right? Same excited state. This one we keep going up that vibration, or we keep going up into another electronic excited state. Same thing here. But what about the case, like maybe we have two different levels for a different reason. Maybe we have two different levels because one of them is like a symmetric stretch and the other one is an asymmetric stretch, anti-symmetric stretch. These are two different vibrational levels. They're both coupled to each other. They share a common ground state. We've talked about this before. We even talked about how you can get anharmonic coupling. So let's see how that shows up in a 2D spectrum or in a third order response. Again, with this sequence, then we're going to come up on the left, up to the right. We have 0, 0. We end up in A0 as our first coherence. And then the arrow on the left is going to bring us back to the ground state. 0, 0. And then now we have our K3, which is positive. We go up, and we have B0. And our signal is this one. So what do we see here? This frequency is omega A0. This frequency is omega B0. And then we're in the ground state in between. Right? So if you did an experiment like this, where you scan the time delay between these two, cause the signal to oscillate at the frequency A0, but you detected light at the frequency B0, this is the light that goes to our detector, then what you'll see is what we call a cross peak. Let's make this the lower frequency one, omega A0. This is omega B0. The detection will be like this. This is omega B0 and omega A0. All right. So this corresponds to exciting omega A0 and detecting omega B0, which is a peak right here. Okay. Well, if I just swap A and B, because nothing told me I had to only go to A here. If I swap A and B, I'll get the other cross peak too. Right? And those are the cross peaks. These show up on the diagonal in a two-dimensional representation. And this shows up below the diagonal because the frequency is lower. Right? So these are all diagonal. This one's a cross peak. And this is like a cross peak, but it's below what I'll say below diagonal, because it still only involves the same mode, just an excited state of that same mode. So in this case, the spectrum would look like you have the line from where the frequencies are equal to each other. You have the first state and the second one. Now we first get to our importance about the number of interactions on the bra side. Remember, it's the ket on the left and the bra on the right. Because of the commutators, you can work this out for yourself. The overall sign of each diagram will be -1 to the number of bra side interactions. Okay, so when n is 1, like it is here, this sign is -1. Here we have 2, so it's -1 squared. So the overall sign is 1. Same thing here, there's 0, so -1 to the 0 is also 1. Here they're also 0, so the -1. So in our parentheses, we see that the ESA signal has the opposite sign of all the other ones. That allows us to understand that actually when we plot this, we should use two different colors to indicate there's a positive sign for one signal, let's say the one on the diagonal, and then a negative sign for the excited state absorption. or vice versa, depending on whether you like to think of it as absorption or the inverse of absorption. You can always multiply everything by -1, it doesn't change anything. Okay, so these are cross peaks, and I want you to notice the phases are the same, meaning the frequencies of these frequencies are the same sign, have the same sign. Why am I making a big deal about that? Because for the other pathway that we need to consider, it will be different. All right, so let's work that out. So the other pathway that's important for understanding the modern multidimensional spectroscopy is this one, where you have a minus K1 plus K2 plus K3. There's a third one that I'll tell you about, of course. All right, so let's work it out in analogy to this one here. We have our arrows, so this is minus, it goes this way, this is plus, and this is plus. Okay, so we're going to make our diagrams. The first one was this ground state bleaching signal. Now, instead of going up to the right, we're going to come up from the right, because the system is in the ground state again, we presume. There's nothing wrong with having it be in a Boltzmann distribution. It just means you're going to have to add up many pathways, including the ones where it doesn't start in the ground state. Okay, so then there's that, and then plus K2. So plus K2 is an arrow pointing this way. So for us, that means, to make the analogy with this one, it's going back to the ground state, 0A, 0, 0. And then plus K3. There's only one way to go plus K3, that's over here. That goes up to A, 0. And then the final trace is down to 0, 0. All right, so what do we see? There's something similar and something different here. First, we notice that the population part, or what we call the waiting time period, the middle time evolution period, it occurs on the ground state, which is what we saw in this case here, of course. What I want you to notice is the frequencies. This is omega 0A, and this is omega A0. Right? The magnitude of those frequencies is the same, but the sign is not. So here we're going to have e to the minus I omega 0A T1, this is T1, T1 for that Green's function. And up here we're going to have e to the plus I omega 0A T3. What that tells us is the sign of the coherence, or the phase of the coherence in the emission time, T3, is opposite the phase of the excitation time. These phases are opposite. Pi phase shift. Another way of thinking about this, and this is the one that's the most illuminating, is to say, no, the frequencies are the same. It's the time that's different. So what sometimes people will do is they'll use the terminology that this third, the second pulse that comes in, the third pulse that comes in creates a coherence that is time reversal, the time reversed version of the coherence that made the excitation. All right, and so this time reversal could allow, and it does in fact allow, a rephasing of the inhomogeneous distribution of frequencies that you have in your experiment. And that's probably the most important aspect of this experiment here. I'll come up with a different metaphor for that in the final lecture segment when I talk about that. The important thing to realize is these two phases are opposite. Sometimes this is called phase conjugation. And this is a very general principle in optics. People use this property even for making mirrors. There's something called the phase conjugate mirror. And it basically involves a way of reversing time evolution by, in this case, just selecting which signal direction you're looking. All right, and so this is what's going to allow us to undo an inhomogeneously broadened distribution of oscillators to bring them back into phase with each other and create what's called a photon echo. Now, this was not originally discovered in optics. It was originally discovered in NMR, making something called a spin echo, but with the same exact principles. So what a lot of people do is compare the photon echo pathway with the non-echo pathway. Notice that the frequencies are not opposite from each other, or negatives of each other. So there's no undoing of the time evolution by this interaction. This is the photon echo. We call this pathway overall, this whole pathway, all the possible ones, we call this a rephasing pathway, because it allows you to undo the time evolution to a certain extent that happened during the first period. Now, we don't have a fancy name for this one, so we give it a stupid name. We call it non-rephasing, which is frustrating. We could have called it the dephasing pathway, because it only shows us the amount of dephasing that we get. So by subtracting literally the signal you get from this signal you get from that, you can actually recover the signal that comes from the reversibility of the dynamics. All right, so that's one of the pathways that corresponds to this sort of ground state bleach. Let's look at all the other ones. All right, so we have the excited state absorption. Let's just do this one here. The stimulated emission pathway. All right, so it's going to go up. We need to make an excited state population. So up, 0, 0, 0, A. And then to make the analogy with this one, we go down, because we still have our arrow pointing up to the right. So we have A, 0, and then this is our signal here, 0, 0. So here we have omega 0A, and here we have omega A0. Again, they're conjugates of each other, so this is going to make an echo. It could if you have inhomogeneous broadening, but now you're on the excited state. So you can wonder, will the dynamics be the same in the excited state as they are in the ground state? For many vibrational cases, that's a reasonable guess. I would say for probably no electronic spectrum cases is that a reasonable guess. Some people seem to be interested in trying to interpret their data this way anyway. That's a caveat. Be careful that when you look at the peak on the diagonal that corresponds to the same peak in your linear absorption spectrum, you want to interpret it this way in terms of this rephasing, which is actually how we can get the frequency correlation function. But actually, if your system is not at equilibrium, this is a problem. Remember, we started our entire Kubo line shape hypothesis by supposing that the frequency fluctuations are stationary. They're at equilibrium. All right, so let's keep going with this one here. No, let's go with this one here before we get to the cross peak one. All right, so we look at the below the diagonal signal. It's going to look pretty similar. We start over here, we go over here, and now we're going to keep going up. So K3 is with a plus, right? Because we have minus K1 plus K2 plus K3. We have 0A. And then we make an excited state population, and then we make an excited state absorption, and then the signal comes back to the A state and stays on the population there. All right, frequency, omega 0A and omega BA. Now, generally, these will not overlap in the same spectral range, and so they will be separate peaks. This is in the excited state. All right, and then the fourth pathway that we've been considering is this one over here. All right, we have 0, 0, go up. And this is the one where we go back down again. And then we come up on the other side. And then we go down. Frequency omega 0A. Frequency omega B0, and we're on the ground state in the middle. This corresponds to a cross peak. Right, exactly the same way as it did in the non-rephasing case. Here we've excited 0A. Let's say A is lower, so that means we get the peak over here. And then we can, of course, get the opposite one when we switch A and B. Right, so these are cross peaks. This is a below the diagonal if it's vibrations. If it's electronic, it could be anywhere. If it's a particle in the box, it's above. This is the on the diagonal, no matter what kind of spectroscopy you do. And again, this is also on the diagonal. All right. Now let's talk about one final set of pathways here for this diagram. And that is ones where when we make the excited state, or after the second interaction, instead of going from A on the left and A on the right, we go A here, but we put it to B on the right. There's no reason we can't do that as long as there's a transition dipole moment for that. So I'll consider the two different ways of doing that with rephasing and non-rephasing. So first we'll do it with the non-rephasing. Okay, so just remind yourself it's this set of arrows. So from the left, we're going to go to A, 0, 0, 0. Then instead of going to A, we're going to go to B on the right. All right, and then we can do whatever we want afterwards, but let's do, it's going to go back to the ground state, A, 0, and then this goes back to 0, 0. So our frequency is omega A0 for the excitation and omega A0 for the detection. Same frequency. So this is a diagonal peak. Gosh, I cannot write diagonal. That's my problem. All right, diagonal peak. But notice that instead of being in the ground state or an excited state population, it's actually in a coherence in the excited state. And we see this first example of making a kind of wave packet. And we know what's going to happen. We've seen so many examples of this, right? Iodine from that amazing paper by Kent Wilson. And we've seen all the different isomerizing molecules where we make coherences. And then I showed you all the work with the super ridiculously short pulses from Kobayashi and Cerullo and all the people who have extremely short pulses. And now, of course, in the photosynthesis community, where they look at coherences all the time in photosynthesis, and we do it also in infrared spectroscopy, metal carbonyls. Anywhere there's coupling and bands are split and you have pulses that are broad enough, you can create these coherences and you can watch them decay because they have a frequency. Now I have to add a frequency here, omega A B. And they'll have a dephasing as well. And you can ask yourself, is the dephasing mechanism of this coherence the same as the dephasing mechanism of that one? Remember, because you're thinking about it from a Kubo line shape, or you're thinking of it from a spectral density, which is what leads to all these de-relaxations in the first place. And that's still an active area of research. In our experience, we find that in the metal carbonyl case anyway, that the decays of these coherences within the excited states decay basically the same as you would expect from the ground state coherences. Let's look up the rephasing, which I'll just abbreviate with R. All right, so we start from the other side now. We have 0, 0, 0A, BA. Then we're going to go down here, B0, and the final signal takes you back to 0. Now notice here, we're exciting omega A0A, sorry. We're detecting omega B0. And our excited state coherence is omega BA. All right, so what do we notice about this? The main thing that we notice is that this is a cross peak. Whereas in the case of the non-rephasing spectrum, it's a diagonal peak. Now, something that I'm not going to explain to you, but you can ask me about offline, is that there's another kind of spectrum that we can make in multidimensional spectroscopy that comes from adding a rephasing plus a non-rephasing to make what's called, we call an absorptive spectrum. And so when you do that, you add together non-rephasing and rephasing pathways. So what that means is if the diagonal peaks oscillate when you have coherence in a non-rephasing, and the cross peaks oscillate when you have a rephasing, when you add them together, in principle, all the peaks could be oscillating. Right? And that's what happens in many experiments when you have broadband pulses that you excite with and relatively narrow transitions. And it turns out there's some convenience in being able to separate out rephasing and non-rephasing if you're interested in analyzing these coherences. That becomes a little bit more tricky when people use the pump probe geometry. But when you have a pulse shaper to do it, then it's straightforward to separate out these again. All right, so then what you see here is that we can measure these coherences by looking at a point in the 2D spectrum. For the case of rephasing, you look at exciting omega A, or 0A, and detecting omega 0B, and you'll see this cross peak here. And the idea is if you could look at its amplitude as a function of time, you would see it oscillates. So I show you an example here from our work. It's very, very, very clear when you see these oscillations. You can take the Fourier transform of those, and what you should see is you should see the difference in frequency between the excitation and the detection step. That's it. That's what you should see. No matter how many states you have in your system. Because this location in the 2D spectrum, you know you excited this frequency, you know you detected that frequency, you know you make this coherence, and that should be all there is. Now what we've seen, actually since we started doing this more than 10 years ago, is that you often see much more than one frequency. You often see 2 or 3 frequencies. And what we've learned over the years is that this comes from the breakdown in the so-called secular approximation in red field theory. And so that's a whole area, a topic of research that we're working on in my group right now. Other people in other contexts are interested in that idea as well. And you would never know if you looked at just a pump probe spectrum, because you would not be able to separate out excitation and detection frequency the way we can here. If you use a narrowband pump to select the frequency range, you wouldn't have enough bandwidth to create a coherence in the first place. Now, if you don't like the coherences, that's a good way to do it. But if you want to use short pulses to have the highest time resolution, you're going to end up with these coherences, whether you like them or not. Okay, so this is really how you put it all together. This is how you go from time-dependent quantum mechanics, red field theory for relaxation. There's more fancy ones than this, but this is a good way to think about it. A Kubo line-shaped theory if you like to have something a little bit more phenomenological. Second order or nth order perturbation theory for the evolution of a system with those fields. And then a diagrammatic method to list all of the different terms in the perturbation theory expansion that you need to add together to make the signal that you detect or calculate, one or the other. And the nice thing is now I can go and look at a 2D spectrum and tell you exactly what all of the different peaks correspond to as far as these different Feynman pathways or Liouville space pathways. And I'll probably as a separate lecture segment that's not part of the course, I will walk through how to look at a 2D spectrum and interpret it in terms of all of the different pathways. We can work out every single one for one representative 2D spectrum. Right? And that would be a good background for anyone who's interested in learning more about this field. All right, so for now, I will do one final lecture segment on the photon echo, but otherwise that's it for Chem 580. It was an unusual semester, as I'm sure it is for everybody. But it was nice to be able to have a chance at least to get these lectures down on and recorded. And so if they could be a useful resource to anyone else, especially the younger generation, a newer generation who is forging ahead with more stable, high rep rate, reliable lasers that will not cause you trouble. The possibilities of new kinds of experiments by combining different pulses, different frequency ranges, combine them with really interesting sample methods of preparation of samples. My lab is doing electrochemistry. You can do other things. There's a huge future in this, and the trick is learning how to translate the chemistry, the dynamics, and the information of the spectrum into actual chemistry. And that is not as easy as it seems. We struggle with this all the time. But that's the one area where I would say I have faith here. I don't like that term to use in science, but I have faith that this is the right path. I could be wrong though, right? And so maybe that turns out that there is not a real clear way for ultra-fast spectroscopists to link to chemistry, but I hope it is. Let me put it that way. I hope that there is a way to make predictive understanding stronger in chemistry by making better and better measurements of what molecules actually do. And this is probably the best way to do it in the condensed phase. All right, take care.